And today I'm just going to talk about some things for your big data toolbox. As Devash has pointed out, big data is typically much bigger than what a lot of us work with on a daily basis here at the School of Medicine. But a lot of the problems and a lot of the tools for solving the problems are the same, whether you're doing it on your computer or on a remote cloud computer, if you will. So I'm just going to point out some of those, talk about a few examples, and then hopefully if you have more questions, we can just get into a discussion as we go. So these are just some things that I use and that are out there. It's not in any way, I guess, covering the whole field, but if you're going to get into the world of big data, you're going to need skills for handling and storing big data, or you're going to need access to people who do this for a living. And so there's, people on this campus who have the capability, servers, clusters of computers that are sort of aligned in parallel. But if we're talking about big genomics data sets from, say, an app you've developed for your project and you're collecting lots and lots of data on your patients, one option could be cloud services. So I'll get into each of these. So tools you'll need from a data management and data analysis perspective. R is free. It's very powerful. Some people argue that R isn't very good at data management. I disagree. I think it's great for that. And the real advantage is the network of people who produce, code for R. So it's an open source software. There's a site called the Comprehensive R Archive Network, and this is where a lot of statisticians across the country are contributing their work. So if you want the newest machine learning algorithms and you don't want to wait half a decade for SAS to come out with a proc for it, R is a good alternative. And I happen to collaborate a lot globally, and so if my collaborators are in Mozambique, for example, they can't really use SAS. So it's great for that. Another program that's out there is Python. Python is very easy to learn. It's also free, and it also has a large suite of machine learning algorithms and just modern algorithms that are being developed by statisticians around the country and actually around the globe. So I think we're actually moving in a direction where free software is going to really be the norm, because having worked as an independent contractor previously, I simply didn't have the option of using a single SAS license. So I think these are skills that you can learn. There are classes now on this campus. Devashis has just taught the first R Python combination course last spring. And there's a lot of online resources for learning these programs. So Coursera has lots of different courses on Python and R, basic programming courses, but they also have R for machine learning, Python for machine learning. And then the last bullet I didn't point out, this is actually an online master's degree you can get at the University of California, Berkeley, which is a Master's of Information and Data Science. And then the book at the top is a very handy book. And even if you're not doing machine learning algorithms, in a sense, there's a lot of concepts in machine learning that allow you to work with big data that make it easier to work with. And I'll talk about that on my last slide. So if you are working with big data and you can't, say, do everything you need to do on your computer, there's cloud-based services, and they're not free. You have to pay into them, but they're really useful because you can pay for what you use, the resources you use. So during my postdoc, I worked with the Institute for Disease Modeling in Seattle. It's a group that develops models for transition modeling of HIV, polio, and malaria, and we were funded by Bill Gates. And we had a room full of very large servers, but we outgrew that very quickly. So this is just to say that very few people, even if you're funded by Bill Gates, can afford to have a room of very large computers and have that last. So the idea of cloud computing is to use this distributed cloud computing called Hadoop. Hadoop is a way of accessing many different computers that exist somewhere not on your campus that you can access and use to run your jobs, if you will. And then when you're done paying. So you pay into a service, but you pay for what you're utilizing. This, I think, is the direction that people are really going to be going, because we're going to outgrow our desktops and our laptops, and we certainly did during my postdoc, and so we actually rented space from a group in Florida who had big servers, sent out jobs to computers that were accessed in parallel. And so a lot of these big companies we all know about have cloud services. So I encourage you, now I guess one caveat is there doesn't exist a cloud service that can guarantee that they can host PHI, okay? That is something you kind of have to work out as you go with CoMERB and your grant, but there really isn't a guarantee of any sort of safety, but there's no guarantee that on your laptop it's safe either. So really, that's something I would say is difficult, but you can overcome in public health. So this is just something I wanted to talk about conceptually with big data. So we have big data, but it doesn't have to be big when we're analyzing it, right? There are ways of saying, I have, hundreds of thousands of covariates, and really I don't care about all of them. Is there a way I can reduce this to something that's a little more useful? And if anyone in here has taken an undergraduate course in linear algebra, you should be familiar with the singular value decomposition. So this is used in almost every algorithm you can think of. It's how we get least squares. And basically what it does is find the minimal amount of your massive data set that can describe everything in your data set. Okay, so you think of a linear combination of variables can be equivalent to maybe one thing, and that is exactly what principal components analysis is too. It relies on the theory of singular value decomposition. So principal components are exactly as they sound. What are the components of my data set that can represent the full data? An example of this, every 4 years in most African countries, they do a demographic health survey. This is a cluster survey of about 600 clusters throughout the country, where they go and administer a survey. They test people for HIV and malaria, and they ask all kinds of questions, probably questions that seem a little bit radical to Americans, but like, how many goats do you have? How many cows do you have? Do you have a cement floor or a dirt floor? Do you have running water? These things. But in the end, you get this data set, and are you really interested at all in how many cows a person has? Not really. But what we want to know is, what is that person's socioeconomic status? And so we can ask variables that are relevant to that and use principal components analysis to sort of break that down into what we call socioeconomic levels. And so what this company does, who administers this survey, is apply principal components analysis to get a 5-level socioeconomic status indicator for all the people in Africa. This is very handy, because if you have socioeconomic status, you've got their HIV positivity rate or malaria status, you can use that instead of 50-some covariates in a model. You've got one variable that represents all 50 of those other covariates. This is done a lot in genomics as well. So those are just some ideas, I guess, to touch on I guess I'll just give a couple examples of some big data I've worked with and some of the challenges. So there was a big mass screen and treat campaign in Zambia about a handful of years ago, where the idea was to go into communities, about 90,000 people, screen them for malaria, and treat everyone that was positive. And then come back about 3 months later and do it again, 3 months later and do it again. And so you're collecting 90,000 blood samples, people's names, generating an ID number for people. And then they asked me to sort of look, if we could look back longitudinally, because these are communities of people who aren't moving very often, and actually match these people. And unfortunately, this ID number that they were assigning changed every 3 months. And in Africa, people have the same names, especially in Zambia. There's a lot of names like peace, hope, beauty, like things that are sort of, I don't know, religiously based, but not. So there's that challenge, a lot of the same names, and then the challenge of sometimes we put the first name in the last name column or the last name in the first name column. And so this really was a record linkage issue that Tal mentioned. And so one of the tools that was really handy in that situation is structured query language. It's a way of linking. I'm sure Tone is very familiar with SQL code. So SQL code is something that can do fuzzy merges. Okay, so there's things like sounds like operator. Okay, so if you have one column that sounds like another column, you can try to merge on that. So that was a messy data situation where there's a tool that can be useful. You still end up probably with about 40% of your data not being able to be linked. But you know, there are tools out there. Sometimes they work, sometimes they don't. And then I think the other one I was going to, I guess one of the advantages to working with data from Africa, it can be missing a lot, but they do have, especially for HIV, set up every clinic in the country of Mozambique or Zambia or Zimbabwe, wherever you're working, has one system for collecting information on HIV data. So if you are in one province and you go to another province, you have a unique ID and that can be linked. And everybody is collecting data in the same system. So you have all the same covariates on everyone. You have all the same treatment measures on everyone. And I think in the US, it's a disadvantage. So I think a lot of these countries where their systems are new, they've learned from everyone else how to set this up in a way that we can collect the same indicators from everyone. In the US, we're so established now that there's really no way of going back and changing that. But there are things like EPIC here at the University of Colorado, the All Payers Claims Database, and these things can be linked within the system. So the University of Colorado, we're linking all payer claims, EHR, and the National Surgical Quality Improvement data pretty easily within the system. So I think there's a precedence, we're trying, but I think nationally it's very difficult, and you're going to have the tools to deal with trying to link records and trying to manage big data. So that's all I have. Any